Alright, so we started Unit 3 on Wednesday when we did the whole YouTube activity, and we'll go over that more in detail on Monday when we come back. But to recap, Unit 3 is going to be called bonding, and we're going to take a closer look at what happens when the elements on the table combine with one another. Because again, by themselves, they're pretty mundane and ordinary, but when we start combining them, they make pretty extraordinary things. And it's going to also be pretty cool because when you walk out of this unit, you're going to know a new language. We call that nomenclature, chemical nomenclature, to be specific. So some people call it like chemistry-nese. So if you're bilingual already, you're going to be trilingual in a couple of weeks, and you're welcome for that. But the first section is just going to specifically look at chemical structure and the different ways that elements can actually combine with one another. We're going to look at 3 in specific. First, let's go ahead and recall the YouTube activity that we had done. So in that lab, we proved that elements combine. Now, how did we do this? Okay, so first of all, we observed solid copper 2 chloride. It was a green material in the evaporating dish. It looked like a bunch of little tiny crystals. We tried to test it with that conductivity meter, and we found out that it was not conductive, like whatsoever. So we then took that copper 2 chloride and we dissolved it in water. Now, I should preface this by saying water was distilled water. Distilled water is not conductive either. So we took a non-conductive solid, copper 2 chloride, and a non-conductive liquid, distilled water, and we combined the two of them, and we got a conductive solution. So what's going on here? Well, what happens is when we dissolve a ionic compound, which I'll define in a little bit, we create things called ions. And we talked about ions in Unit 2. So those are charged atoms. They're either positively or negatively charged because they've either gained or lost electrons. In the case of the lab, the copper atoms had lost electrons, and the chlorine atoms had gained electrons. So we also observed the separation of the ions from the solution, because I didn't just want you to take my word for it that there were little ions in there that the copper and the chlorine were swimming throughout the solution. We ran electricity through the solution. We used graphite rods in the 9-volt battery, and you should have seen an accumulation of like a reddish-brownish substance on one of the electrodes, and an accumulation of bubbles and an odor on the other electrode. Now the chlorine was the odorous electrode, and that electrode happened to be positive. So if we reflect on that, that must mean that chlorine itself is the negative thing. Chlorine is the thing that is accepting the electrons or taking in new electrons. On the other hand, copper went to the negative clip. And we always know that opposites attract. So copper is positive, okay, because it went to the negative clip, and chlorine is negative because it went to the positive clip. So copper and chlorine, they should come together as ions. They don't in water, they stay separated, but if we were to evaporate the water in that U-tube, we would have gotten that crystalline green substance back, just like that. So if you're a little fuzzy on what it looked like again, we'll show it again on Monday, because I actually let one of them sit throughout the entire weekend, so the accumulation of copper is going to be pretty awesome, and you'll see a distinct color change of the liquid solution. But this is what it looked like, and again, you had positive copper ions on the negative electrode, and you had the negative chloride ions on the positive electrode. And if you let this run long enough, you're going to see a distinct change in the U-tube color itself. So we'll take a look at that U-tube again on Monday just to kind of reflect on it, and then there are some analysis questions in the lab that we'll finish up. All right, so again, let's focus on that first type of compound, the type that copper chloride is, which is called the ionic compound. These are compounds that are by definition made of metals and nonmetals. And what these metals and nonmetals do is they will transfer their electrons between one another. So one wants electrons, excuse me, and the other doesn't want electrons. When they form, like if you think about like sodium chloride, which sodium's a metal because it's on the left side of the periodic table, chlorine is obviously a nonmetal. Sodium chloride, when they form, you don't think of just like one sodium atom and one chlorine atom coming together and forming. Instead, you've got like a billion sodium atoms and a billion chlorine atoms, and that's even underestimating, that come together and they form what's called a lattice structure. And this is what a lattice would look like. And this is actually a lattice structure. Actually not quite sure. I don't think it is copper chloride. No, it's certainly not. But a lattice structure looks like you've got a whole bunch of different elements that are in that particular compound. So if it were copper chloride, you'd have copper and chlorine. and they all bond with each other. One of the types of elements is gaining electrons, the other is losing electrons, and they all kind of do the same thing. They do the same dance. So at the end of the day, what you have is a copper atom with a positive charge and a chlorine atom with a negative charge. Maybe a chlorine atom down here with a negative charge and a copper atom down here with a positive charge. And we get a whole bunch of bonding. We get like a bond there, a bond there, a bond there, a bond there, and they all kind of bond together. All right. So that's what the copper chloride would look like. It gets that crystalline shape every time the lattice is formed in these ionic compounds. Now, the ratio of elements in the lattice will actually give us something called the chemical formula, and we'll learn that in a future unit. But like for instance, salt, table salt, is just NaCl. So that means there's one sodium atom for every chlorine atom, 1 to 1. Now the stuff that we worked with last Wednesday, copper 2 chloride, now that's one copper atom for every 2 chlorine atoms. Again, that doesn't mean that there's just one copper atom and 2 chlorine atoms. No, that means that there's like 1 billion copper atoms and 2 billion chlorine atoms. But the ratio always holds true. Okay. What this lattice concept leads to is ionic compounds have incredibly high melting points. And if you think about the minerals that we dig up from the ground, usually they're rocky substances, or you think about table salt itself, you don't think about those things melting very easily. And in fact, they don't. They have very, very high melting points. And that's due to the fact that there's really high electrostatic attractions between the ions that are involved in the lattice. All right, let's go to the second type of compound now, which is called a covalent compound. Sometimes you'll hear these referred to as molecular compounds. Now, these things typically do not conduct electricity. There are some cases where they do, like organic acids, for instance. But typically they do not conduct electricity. They're composed of non-metallic elements. Non-metallic elements. So if you think of like the stuff you're breathing out right now as you listen to this video, carbon dioxide, or the stuff you're breathing in, oxygen, which is 2 oxygen atoms bound together. Those particular molecules are combined using something called a covalent bond. And a covalent bond is actually due to the sharing of electrons instead of the transfer of electrons. When molecular solids, so sometimes these things can be in solid form, like wax is a really good example of a compound that is covalently bonded. When they're dissolved or melted, they break into neutral molecules. So, like when we dissolve salt, it breaks into ions. That does not happen with covalent compounds. When we have like sugar, for instance, okay, here's an example of sugar, and you can see table sugar in your hand, and you add a little bit of heat to it, and it breaks down into 2 separate sugar molecules. So when you liquefy it, if you're making something that requires the sugar to be liquefied. Okay, and so what happens is instead of making ions, we essentially just break apart the 2 sugar molecules that were connected. This breakage can occur at pretty low melting points because the attraction that originally bonded the 2 molecules together was relatively low. And I want to go back to what I said previously, is that covalent compounds themselves are formed not by the transfer of electrons, instead of by the sharing of electrons. The transfer of electrons would create ions. Sharing of electrons does not. It forms a more symbiotic relationship between the 2 elements that are involved, and they oftentimes will stay together. All right, the last type of bond then is going to be called a metallic bond, probably the one that you're influenced by most in life, the one that you can see most easily. Metals gain their structure using metallic bonding, and so if you got any metals around, like a water bottle or your desk chair that you sit in class, the legs of the chairs there, metals are all around us. And metallic bonding happens when the valence electrons of a large group of atoms are shared, essentially, between all atoms. And chemists often call this a sea of electrons. So the image in the lower right-hand corner is pretty good. If you think about a whole bunch of iron nuclei, that's the big gray circles with plus signs in them, and they're all clumped together. And their valence electrons are the red little electrons that are on the outside. They just kind of play hot potato with those electrons. They pass them back and forth from one atom to another atom to another atom. This causes partial positive and partial negative charges. Now, this particular property really helps to explain why metals are such good electrical conductors. Also helps to explain why they're good conductors of heat. There are already electrons moving throughout the metallic substance. So if you place an electrical current on a metal, that's just going to expedite the movement of those electrons. And if you're touching that piece of metal, those electrons will then, unfortunately, move to you. All right, so that's going to be the end of 3.1.